Hello, and welcome to this video about the number line. In this video, we will explore how to read number lines, draw and plot points on a number line, and add and subtract with a number line. Let's get started. We will use a number line to represent numbers in counting order. The number to the left is always smaller than the number to its right. To draw a number line, we first start by drawing a straight line, and then we put arrows at the ends. The arrows represent the fact that the number line goes on forever in both directions. When dividing the number line with tick marks, it is important to place the tick marks equally spaced apart. This shows that the distance from any two numbers is the same. For example, the distance from 1 to 2 is the same as the distance from 2 to 3. The most important number on a number line is 0, because every other number is based off of how far away it is from 0. Numbers to the left of 0 are negative, and numbers to the right of 0 are positive. Number lines continue infinitely in either direction, so the number line you see is always only part of the whole number line. Because of this, even though 0 is the most important number, it might not show up on your number line. For example, your number line might look like this if you're trying to plot the grade you got on your test. Number lines can be used to represent a specific number. In the example we just mentioned, we can use the number line to represent a test grade of 94 by putting a dot above the number like this. Plotting a negative number would happen the same way. Simply put a dot over the number you are wanting to represent. The number line here shows the number -5. We can also use a number line to help us add and subtract numbers. Movement to the right is for addition, and movement to the left is for subtraction. To use the number line for adding and subtracting, we start by plotting a point at our first number. Then we move right or left, depending on the operation, the number of spaces matching the second number. Let's practice by adding -7 plus 5. We will start at -7, and since the operation is addition, we will move to the right 5 spaces. As you can see, we land on -2. Therefore, -7 plus 5 equals -2. Now let's try subtracting 9 minus 4. We will start at the number 9 on the number line, and since the operation is subtraction, this time we're going to move to the left. We move left 4 spaces, which lands us on 5. Therefore, 9 minus 4 equals 5. Hi, and welcome to this video about absolute value. We'll cover what the absolute value of a number is and how to calculate it, as well as what absolute difference is and how it relates to absolute value. Let's get started. The absolute value of a number is its distance from 0 on a number line. Let's use the number 6 as an example. Using a number line, we can see that 6 is 1, 2, 3, 4, 5, 6 places away from 0. Therefore, the absolute value of 6 is 6. -6 is also 1, 2, 3, 4, 5, 6 units away from 0. Therefore, the absolute value of -6 is also 6. Absolute value has a specific notation in mathematical expressions. For instance, the absolute value of 6 is denoted with 2 vertical lines here and here. And the absolute value of -6 is denoted as a -6 with lines on either side, just as before. Now, just as we saw, the absolute value of 6 equals 6. And the absolute value of -6 also equals 6. No matter what number you are dealing with, big or large, positive or negative, the absolute value operation always yields a positive number. This is good to remember when evaluating expressions and solving equations, but it's also important to remember why. When we talk about distance, the direction doesn't matter. In everyday language, we wouldn't say, for instance, the grocery store is -1 mile away. We'd simply say the grocery store is a mile away. Similarly, on the number line, we are simply counting distance without specifying direction. So the absolute value of -7 is equal to 7. Literally, this translates as -7 is 7 units away from 0. When we evaluate expressions and solve equations, the absolute value brackets act very much like parentheses do in the order of operations. We evaluate what's inside the absolute value brackets first. Let's look at a simple example. 1 minus the absolute value of 2 plus -5. We evaluate what's inside the brackets first. So 2 plus -5 equals -3, which gives us 1 minus the absolute value of -3. Using our number line, we can see that -3 is 3 units away from 0, which means that the absolute value of negative 3 is 3. This gives us 1 minus 3, which equals negative 2. Since absolute value is a calculation of a number's distance from 0, an absolute value expression, such as the absolute value of 3, can be written as the absolute value of 3 minus 0. Another way to interpret this statement is by saying the distance between 3 and 0 is 3. Writing it this way provides the same result. The second number here doesn't need to be 0 though. We can actually calculate the distance between any two numbers. On the number line, we can see the distance between negative 2 and 8 is 10. As an expression, we might write this as the absolute value of negative 2 minus 8 equals 10. This is called an absolute difference. Now let's do a quick recap. The absolute value of a number is its distance from 0 on a number line. And regardless of what number you're working with, the answer will always be a positive number. The absolute difference is used to calculate the distance between any two numbers on the number line, not just a number and 0. Hey guys! Today we're going to take a look at the mathematical operations addition, subtraction, multiplication, and division. These four operations serve as the fundamental building blocks for all math, so it is crucial to have a solid understanding to build upon. Let's dive in. We use addition and subtraction to solve many real-world situations. Addition and subtraction are simply the mathematical terms used to describe combining and taking away. When we add, we are combining or increasing. When we subtract, we are taking away or decreasing. As a reminder, the symbol we use for addition is a plus sign. The answer to an addition problem is called the sum. The symbol we use for subtraction is a minus sign. And the answer to a subtraction problem is called the difference. Essentially, addition and subtraction are opposite operations. One adds value and the other deducts value. One strategy for visualizing these two operations is to use a number line. We will use a number line to illustrate the following examples. Let's imagine a situation that involves the sale of popcorn. For this scenario, let's assume that you are trying to raise money by selling bags of popcorn and you start with 20 bags. When your first customer arrives, they wish to purchase 4 bags of popcorn. This means that your remaining number of bags will decrease. We can represent this situation with a simple equation that involves subtraction. We started with 20 bags and we decreased by 4 or subtracted 4. Our subtraction equation is written as 20 minus 4 equals 16. On a number line, we can represent this deduction by starting at 20 and then moving backwards 4 units in the negative direction. Each jump backwards represents subtraction by 1. Now let's say you started with 20 bags of popcorn and ended up with 6 bags left at the end of the day. You need to replenish your stock in order to keep up your sales, so you make 4 more bags of popcorn. How many bags of popcorn do you now have available to sell? For this scenario, since we are looking at an increase of bags, we will use addition. This situation can be described using the equation 6 plus 4 equals 10. You had 6 bags initially and then combined that amount with 4 more bags. Now you have 10 bags in all. On a number line, addition is represented by jumps to the right in the positive direction. Each jump to the right represents the addition of 1 unit. So in this example, we would be starting at 6 and jumping 4 units to the right. We can see that we land on 10. It is important to notice that when using addition, the order of the values does not matter. For example, 10 plus 30 is the same as 30 plus 10. The placement or arrangement of the values has no effect on the outcome. Both arrangements would equal 40. However, the same is not true for subtraction. Does 30 take away 10 mean the same thing as 10 take away 30? Clearly not. We can see that the order matters when dealing with a situation involving subtraction. The technical term for this quality is known as the commutative property. Essentially, the property is true for operations where the values can move around, commute, and the outcome of the expression or equation will not change. The commutative property applies to addition, but not to subtraction. Another operation that also shares the commutative property is multiplication. Let's discuss multiplication together with division, as we did for addition and subtraction. Multiplication and division are similar to addition and subtraction in that they perform opposite functions. The function of multiplication is to represent multiple groups of a certain value, whereas division is designed to show the separating or subdividing of a value into smaller groups. As a reminder, the symbol we use for multiplication is a times sign. The answer to a multiplication problem is called the product. The symbol we use for division is a division sign, and the answer to a division problem is called the quotient. Multiplication is essentially a convenient and time-efficient way to show what's called repeated addition. For example, if you need to fill 30 bags of popcorn and each bag requires 60 kernels, it could take hours to count up how many kernels you need in total by just using addition. A faster and more efficient way to make this calculation would be to use repeated addition. Instead of counting each seed independently, we would group them up and add the groups together. The calculation would then become 30 groups of 60. This grouping, for the purpose of repeated addition, is the multiplication process at its core. 30 groups of 60 is written as 30 times 60, which is 1,800. So 1,800 kernels are required to fill up 30 bags of popcorn. Both addition and multiplication are commutative because the order does not affect the answer. 30 groups of 60 gets us the same result as 60 groups of 30. Our last operation, division, can be considered multiplication's opposite. When we use division, we are essentially splitting up a large group into smaller subgroups. For our popcorn example, we can use division to answer the following question. How many bags of popcorn can I make using 1,800 kernels if each bag requires 60 seeds? This situation requires us to divide the large value, 1,800, into groups of 60. Each smaller subgroup will now represent a bag of popcorn. 1,800 divided into groups of 60 is represented as 1,800 divided by 60. In this case, the answer is 30, so 30 bags of popcorn can be made with our 1,800 kernels. As you can see, division is not commutative because the order of the values plays a crucial role in determining the answer. 1,800 divided by 60 is not the same thing as 60 divided by 1,800.
Hey guys, welcome to this Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are two different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8. And that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
Hi, and welcome to this video on the properties of exponents. Working with polynomial, radical, and rational functions oftentimes requires us to perform algebraic operations with powers. Recall that a power is nothing more than a base that is raised to an exponent. So let's take a look at the properties of exponents that are used to simplify algebraic expressions with powers. The product of powers property applies to powers with the same base. When asked to multiply powers with the same base, simply add the exponents. For example, b squared times b cubed equals b to the fifth. This rule makes intuitive sense if you expand each power like this. B times b times b times b times b. Counting up the bases of b that are being multiplied results in 1, 2, 3, 4, 5. B to the fifth. Therefore, the general form of the product of powers rule is b to the m times b to the n equals b to the m plus n. The quotient of powers property also applies to powers with the same base. However, the rule requires the subtraction of exponents. Let's look at an example. B to the fifth over b cubed in expanded form would look like this. B times b times b times b times b all over b times b times b. Canceling out common factors of b from the numerator and the denominator would simplify to be b squared. The quotient of powers property allows a quicker, more efficient result. Simply subtract the exponent of the denominator from the exponent of the numerator. 5 minus 3 equals 2. The general form for quotient of powers property is b to the m over b to the n equals b to the m minus n. The power of a power property allows us to raise a power to another exponent. Once again, expanding an expression makes understanding the rule a bit easier. Suppose the power b cubed is squared. In expanded form, it would look like this. B times b times b times b times b times b. Using the product of powers property, or simply counting up the bases of b, results in b to the sixth power. The general form of this property is b to the m raised to the n equals b to the m times n. Expanding on the power of a power property results in additional tools that are used to simplify expressions with powers. For example, suppose the base of a power is a monomial with a coefficient and a variable. 3b to the fourth power squared expands to 3b to the fourth power times 3b to the fourth power. Rearranging the factors to group the coefficients and the powers with the same base, b, and simplifying gives us 3 times 3 times b to the fourth times b to the fourth equals 9b to the eighth. This is called the power of a product property and illustrates that the exponent of each factor in the base must be multiplied by the power outside the parentheses. The general form for the power of product property is b times c to the x equals b to the x times c to the x. The power of quotient property is similar in that the exponent of a rational base is multiplied by the exponents in both the numerator and denominator. Let's look at some examples. B cubed over c squared, all of that squared, expands to b cubed over c squared times b cubed over c squared. The product of powers property results in the simplified expression b to the sixth over c to the fourth. However, applying the power of quotient property directly is often more efficient. B to the third over c squared squared equals b to the 3 times 2 over c to the 2 times 2, which equals b to the 6th over c to the 4th. Here's another example. 2b over c squared d cubed expands to 2b over c squared d times 2b over c squared d, one more time, 2b over c squared d. Rearranging factors and applying the product of powers property results in 2 times 2 times 2 times b times b times b all over c squared times c squared times c squared times d times d times d. This equals 8b cubed over c to the 6th power times d cubed. If we were to apply the power of quotient property, it would look like this. 2 to the 1 times 3 times b to the 1 times 3 all over c to the 2 times 3 times d to the 1 times 3, which equals 2 cubed times b cubed all over c to the 6th times d cubed, which equals 8b cubed all over c to the 6th times d cubed. The general rule for the power of quotient property is b over c to the x equals b to the x over c to the x. As you can see, these rules are essential in simplifying expressions within our work with various algebraic functions.
Hi, and welcome to this video about scientific notation. In this video, we will explore what scientific notation is and how to write and compare numbers in scientific notation. First, what is scientific notation? The idea of scientific notation was developed by Archimedes in the 3rd century BCE, where he outlined a system for calculating the number of grains of sand in the universe, which he found to be 1 followed by 63 zeros. His work was based on place value, a novel concept at the time. Scientific notation is simply a way of writing numbers. It is especially useful in expressing very large or very small numbers because it is shorter and more efficient, and it shows magnitude very easily. Every real number can be written as a product of 2 parts, a decimal part times an integer power of 10. M times 10 to the n, where 1 is less than or equal to m, which is less than 10, and n is an integer. Why 10? Our number system is based on 10, and each place value is 10 times the previous place value. 110 equals 10 ones, 100 equals 10 tens, etc. Let's look at writing large numbers using this notation system. We can write the number 1 as 1 times 10 to the 0. Remember, 10 to the 0 is 1, so this is equal to 1 times 1, which is equal to 1. We can also write the number 13 as 1.3 times 10 to the 1, because 1.3 times 10 is equal to 13. Or we can write the number 134 as 1.34 times 10 squared, because that's equal to 1.34 times 10 times 10. You get 134. Let's look again at Archimedes' findings. He expressed the number of grains of sand in the universe as 1 followed by 63 zeros. We could write that out, but that would take way too long and be highly inefficient. In scientific notation, this would be 1 times 10 to the 63rd power, a much more compact and efficient way of expressing this number. The number of zeros in the gigantic number is represented by the exponent. In the fully written number, it's important to realize that each time we multiply by 10, we move to a new place value. So adding a 0 means multiplying by 10. A light year, the distance light travels in a year, is 5,878,600,000,000 miles. Let's express this in scientific notation. Often, this is described as moving the decimal point, which doesn't actually happen. We simply need to count the number of times we multiply by 10. The decimal part is created from the first block that begins and ends with a non-zero number. In other words, the block can contain a 0, but we don't use the zeros at the end. Our decimal must be greater than or equal to 1 and less than 10. So we always start from the ones place. Here we have 5.8786 times 10 to the something power. This is where we count the number of times our decimal is multiplied by 10. We need to count from the decimal we created to the end of the number. So 5.8786 times 10 to the 1 is equal to 58.786. 5.8786 times 10 squared is equal to 587.86. And then 5.8786 times 10 cubed is equal to 5878.6. And so on until we reach 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 5.8786 times 10 to the 12th. So in scientific notation, a light year can be expressed as 5.8786 times 10 to the 12th miles. But what if you wanted to take a number written using scientific notation and change it into standard form? A light year can also be expressed as 9.4607 times 10 to the 15th meters. We can easily change this number to standard form. Start with the decimal part, 9.4607, and multiply by 10 a total of 15 times. This tells us that a light year is 9,460,700,000,000,000 meters. Let's look at a couple more examples before we move on. If I Google light year, I'm given about 7,380,000,000 search results. Let's express this number in scientific notation. So, as you can see, I was given 7.38 times 10 to the 9th search results. On average, there are 3.72 times 10 to the 13th cells in a human body. Express this number in standard form. The exponent 13 tells us that we have 13 numbers after the decimal, which gives us 3.72 followed by 11 zeros. If we multiply this by 10 13 times, we see that there are 37.2 trillion cells in the human body. So now we know how to write large numbers using scientific notation, but what about small numbers? First, let's recall how negative exponents work. For example, 10 to the negative 1 is equal to 1 over 10 to the first power, which is equal to 1 over 10. And 10 to the negative 2 power is equal to 1 over 10 squared, which is equal to 1 over 100. Where positive exponents represent multiplication, negative exponents represent division. Again, the number 1 can be written as 1 times 10 to the 0 power, which is equal to 1 times 1 equals 1. The number 0.1 can be written as 1 times 10 to the negative 1, which is equal to 1 times 1 over 10, which is equal to 0.1. The number 0.01 can be written as 1 times 10 to the negative second, which is equal to 1 times 1 over 10 squared, which is equal to 1 times 1 over 100, which is equal to 0.01. The wavelength of green light is 0.0000055 meters. Let's see this in scientific notation. We begin the same way as with large numbers, creating the decimal from the chunk bookended by non-zero numbers. Our result will resemble 5.5 times 10 to the negative something power. Now, we count the number of times our decimal is divided by 10. 5.5 times 10 to the negative 1 is equal to 0.55. 5.5 times 10 to the negative second power is equal to 0.055. 5.5 times 10 to the negative third power is equal to 0.0055, and so on until we reach 5.5 times 10 to the 1, 2, 3, 4, 5, 6, 7, negative seventh power. So in scientific notation, the wavelength of green light can be expressed as 5.5 times 10 to the negative seventh meters. The radius of a hydrogen atom is 2.5 times 10 to the negative 11th meters. We can express this in standard form by starting with the decimal part 2.5 and dividing by 10 a total of 11 times. This tells us that the radius of a hydrogen atom is 0.00000000025 meters.
Now, I know what you're thinking. What does this phrase actually mean? Quite a bit, actually, because that saying provides the key to remembering an important math concept: the order of operations. The order of operations is one of the more critical mathematical concepts you'll learn because it dictates how we calculate problems. It gives us a template so that everyone solves math problems the same way. Let's start off with a simple question. What is an operation? An operation is a mathematical action. Addition, subtraction, multiplication, division, and calculating the root are all examples of a mathematical operation. Let's take a look at this problem. Looks easy, right? Well, it wouldn't be so easy if we didn't understand the order in which the math operation occurs. If we didn't have rules to determine what calculations we should make first, we'd come up with different answers. Should you start by subtracting 4 minus 6 and then multiplying by 7? No. The order of operations tells us how to solve a math problem. And this brings us back to Aunt Sally. Operations have a specific order, and this is what Please Excuse My Dear Aunt Sally helps us to understand. It's an acronym PEMDAS, or PEMDAS, that tells us in which order we should solve a mathematical problem. So first is please, which stands for parentheses. So we solve everything inside of the parentheses first. Then E, excuse, which is for exponents. We solve that after we solve everything in a parentheses. Multiplication, which is the my, and this happens from left to right. And then division, which is the dear, which also happens left to right. And then we have addition and subtraction, which also happens from left to right. And this is Aunt and Sally. Okay, so now that we know the order of operations, let's apply it to our problem that we have here and solve. So let's kind of go down our list. We don't have parentheses and we don't have exponents, but we do have multiplication. So we do that before we do any addition and subtraction. So let's go ahead and multiply 7 times 4. That gives us 28. And now we're subtracting 6, which gives us 22. Now let's look at another problem. Without the operations, you could calculate this as 7 plus 7, which is equal to 14, times 3, which is equal to 42. And this would be wrong. Remember, you multiply before you add. Therefore, the equation should look like this. So when we do problems like this, we can use parentheses to group together our numbers that are going to take place first. So in this case, it's 7 times 3. And when we do that, we get 21, and we have plus 7 left over. When we add those together, we get 28, and that's our answer. Let's look at some more complex problems. The order of operations dictates how to solve this problem. Remember, you multiply exponents first. Here's the wrong way to solve the problem. Why is that wrong? Because you violated the order of operations. You do not multiply first. You perform an operation on the exponent first. This is how it should be done. See, solving the equation in the right order provides the correct answer. Let's try out one more problem. This one is a little bit more challenging, but it perfectly illustrates the order of operations. Remember the order. What do we do first? The number inside the parentheses. So 8 times 6 is equal to 48. Then we subtract 15, and that gives us 33. Here's how the problem looks now. So our next step is multiplication and division. So let's perform all of our multiplication and division problems and then see what we have left. Now we finish with addition and subtraction. So here's what we have. And our answer is 37. There is an exception. If an equation only has one expression, you don't have to follow the order of operations. Here are some examples of single expressions. 10 plus 10. Well, there are no other operations, so you just know to go ahead and add them together and you get 20. Same thing with subtraction, multiplication, or division. All of those are single expressions. Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit, I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator. The number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers in their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean. I hope that this overview was helpful to you.